Welcome to today's Explainer, everyone. We're diving straight into Section 9.2 of your software engineering text to look at legacy systems. There's this massive misconception out there that being a software engineer is all about building shiny new applications right from scratch. But honestly, the reality of the industry is completely different. Managing and evolving older, hidden systems that are literally running our global economy is a highly paid, absolutely vital skill. So let's get right into it. Just a quick look at what we'll be covering today. We've got 6 main parts. First, what actually are legacy systems? Then, the famous COBOL problem. We'll look at why we don't just replace them, followed by the high cost of maintenance. After that, we'll cover how to assess and manage these systems, and finally, a summary with some core exam focus points.
Right, Section 1. What are legacy systems?
Before we get into the management side of things, we really need to overturn the idea that older software is just dead code. It's very much alive, so let's define our core term. A legacy system is an older, deeply entrenched system that relies on languages and technology we simply don't use for new systems anymore, but that a business still critically relies upon. We're talking about systems maintained over decades. The structure is probably degraded from years of quick fixes, and they're often running on older hardware, like those massive mainframe computers. But here's where students almost always make a critical mistake. They tend to think legacy systems are just software programs. Actually, they're not. They are what we call socio-technical systems. What does that mean? Well, it's a broader system that includes the hardware, the software, and the libraries, sure, but crucially, it also encompasses the human elements. We're talking about the business processes and the organizational rules wrapped around the technology. You literally cannot separate the technical from the social here. To really grasp the logical parts of a legacy system and how they relate, we have to look at their interactions. It's fascinating because business policies actually constrain the software, and in turn, the application software embeds knowledge of those exact policies. Everything uses or runs on something else. It's a highly interconnected web, so let's break this down methodically. Make sure you get this down for your notes. A legacy system consists of 6 interconnected elements. First up is system hardware. Think old mainframes that might not even be compatible with modern IT setups. Second, support software, which includes operating systems and utilities that might be totally obsolete today. Third is the application software itself, the actual programs doing the heavy lifting. Fourth, application data. This is immense volumes of data accumulated over decades, often inconsistent or duplicated. Fifth, we have business processes. The actual day-to-day tasks, like issuing an insurance policy, which are constrained by the software. And finally, the 6th element, business policies and rules. These are the constraints on the business that are very often hard-coded directly into the old software. So just to recap this part, legacy systems are incredibly complex socio-technical webs, not just a bunch of old code. Moving on to Section 2, the famous COBOL problem. Now that we know the parts of a legacy system, let's look at a real-world example to really understand the massive global scale of this. Take a look at this staggering number. Industry estimates show there are over 200 billion lines of COBOL code still running current business systems today. COBOL was the main business development language from the 1960s right through to the 1990s, especially in finance. These programs still work incredibly efficiently, and honestly, the companies using them see absolutely no reason to change them. But there is a massive problem here, and that's a severe skills shortage. The original developers of these systems, well, they're retiring. On top of that, universities just don't teach this language anymore, because younger engineers obviously want to learn modern languages. This dynamic has created a highly lucrative, highly paid market for engineers who can actually step in, understand COBOL, and maintain this critical infrastructure. Which brings us to Section 3, why not just replace them? This logically leads to the question pretty much every software engineering student asks. Why on earth don't companies just go out, buy a modern system, and replace the old one? Wouldn't that be easier? Well, this introduces us to the replacement paradox. It is actually incredibly risky and wildly expensive to replace them. Let's break down exactly why. First, the original specifications are usually lost or just incomplete. Nobody knows exactly what the old system does anymore. Second, business processes are entirely intertwined with the software. If you replace the software, you basically have to overhaul how the entire business operates. Third, important business rules are embedded deep in the code and aren't documented anywhere else. If you lose those rules, say, the logic for assessing insurance risks, the company could face massive financial ruin. And fourth, new software development is just inherently risky. Your textbook actually mentions a case where an enterprise spent £10 million trying to replace 150 legacy systems with one new ERP system. It completely failed. The new system barely worked, and users had to revert back to the older systems anyway.
Okay, section 4, the high cost of maintenance.
So, replacing them is out of the question because of the risk. But if companies don't replace them, they fall straight into the maintenance trap. Keeping them costs an absolute fortune. But why? Well, first off, over the decades, different people make changes, and that leads to wildly inconsistent programming styles. Second, as we saw with COBOL, the languages are obsolete, meaning companies are forced to pay for really expensive outsourcing just to find developers. Third, the documentation is usually missing or just completely inadequate. In a lot of cases, the source code is literally the only documentation you have left. Fourth, the system structure severely degrades over years of ad hoc changes. This is what we call spaghetti code. And finally, the software was originally optimized for incredibly slow, obsolete hardware. Programmers back then used specific tricks for space or speed optimization that modern engineers just simply do not understand today.
Let's move into section 5, assessing and managing legacy systems. All right, so we can't easily replace them, but they're incredibly expensive to maintain. What do? The core engineering solution here is to systematically categorize and manage that tension. Companies assess their systems using 2 key metrics: technical quality and business value. Technical quality looks at the application itself, plus its environment, like the hardware and the support software. Is the environment stable, or is it crashing all the time? Then, business value is a measure of how much time and effort the system actually saves compared to manual processes. Does the business absolutely depend on the outputs of this system to survive?
By plotting system quality against business value, we can map out 4 distinct strategic clusters for managing legacy systems. Essentially, every legacy system a company owns is going to fall into one of these 4 quadrants. Let's walk through the strategic options for each one of them. First up, the bottom left quadrant. If a system has low technical quality, meaning it is an absolute nightmare to maintain, and low business value, meaning it doesn't really help the business much anymore, the strategic option is pretty straightforward. You just scrap the system completely. The return on investment is way too small to justify keeping it alive.
Second, we have the top left quadrant. What if a system has low technical quality but high business value? This means the system is making a crucial business contribution. It's simply too important to lose. But because the quality is terrible, it's far too fragile and expensive to keep as is. In this specific scenario, you have to re-engineer the system to improve its maintainability, or perhaps replace it with an off-the-shelf product if one exists.
Third is the bottom right quadrant. Here, we're looking at high technical quality but low business value. The system runs beautifully, it doesn't crash, but it doesn't contribute massively to the core goals of the business. For this scenario, we just keep doing regular maintenance. Because the quality is high, the maintenance is cheap. So we leave it running, but we definitely do not spend big money on major changes or upgrades. Finally, the top right quadrant. If a system has both high technical quality and high business value, you're looking at the absolute ideal scenario for a legacy system. It works well, it isn't too expensive to maintain, and it's delivering massive value to the organization. Here, your strategy is to continue normal system maintenance and fiercely protect that asset. That brings us to our final section, summary and exam focus. Let's quickly run through our key takeaways. As your lecturer, I want to make sure you know exactly what to focus on when you're studying for your exams. So please ensure you can do the following. First, be able to clearly define a socio-technical legacy system, and remember to include both the technical and the human elements. Second, you need to list all 6 components: hardware, support software, application data, business processes, and business rules. And third, be able to draw out that quadrant graph we just looked at and explain the 4 strategic options based on business value versus technical quality. That's scrap, re-engineer, or maintain. I also really want you to internalize this critical fact from the text. Original requirements are vital. This quote perfectly reminds us that the system requirements document is genuinely the most important document in system maintenance. Losing this document over the decades is exactly why legacy management and system replacement become such incredibly complex, risky engineering challenges. You simply don't know what the system was originally supposed to do in the first place. To wrap up today's explainer, I want to leave you with a thought to chew on. While working on these older systems isn't always viewed as glamorous work, managing this hidden backbone of the global economy is a highly paid, utterly critical engineering skill. The world's biggest banks, governments, and infrastructures rely entirely on engineers who understand this exact dynamic. So how will you apply this knowledge? Keep that firmly in mind as we prepare for our next topic, where we'll tackle exactly how to execute software reengineering. Thanks for joining me today, and I'll catch you in the next explainer.